Thanks. We are very happy to contribute our part. And as you already said, we are kind of exotic here because we are working with textiles. And we bring these textiles into what we call 4D textiles, which is kind of building on the idea of 4D printing, to be able to design structures with shape-changing behavior with like a lot of energy, because the textile as we use it can bring a lot of energy into the whole system, which allows us bigger change shape. But let's start into our presentation. And what we want to talk to you about today is something that we call 4D textiles with local adhesion. And firstly, we want to quickly give you an introduction about what we have been looking into from a more simulation and modeling side. And by having said this, I also want to mention that we are working from the ITA in Aachen. Xingwen and I are researchers there, and we are collaborating with Marcelo Diaz from the University of Edinburgh. He is an expert in kirigami and origami structures in physics. But let's get back to what we are looking at. We're looking at a linear elastic ribbon that is printed on top of a hyperelastic textile. And that's, as you can see on the left upper side. And what we were becoming interesting in is what actually happens if these both structures are just locally adhering to each other. And what you see on the right upper side now is the behavior that we then discovered, and which we found this was very interesting. What we see here is the reaction when you release the stress that's in a textile, where we printed a ribbon on top. So it contracts and you create this three-dimensional shape. What you color-wise see is the height that we can reach with this system or behavior, and also the amount of pre-stress that was initially applied to the textile, and then it returns back. This overall shape that we can create there, and we decided to have a very simple first model. It's so interesting because we have these proper structures which can result in many different and interesting shapes that we will discover now. I just want to quickly tell you that we are working with a material model that we based on a paper that has been published by the Institute of Textile Technology in Aachen, together with Scott Stapleton. And what is also important to know is that we have an elastic energy in the whole system, but we additionally apply the pre-stress to the textile. That's why we come up with this equation on the right lower side. But having said this about the theory, we want to show you our work in progress and what we have been looking at to understand this material system better. And unmute you, please, too.
Yeah. Can you hear me?
Yes.
Yeah. So we'd like to show you the working process of silicon printing is actually very similar to 3D printing. Here we use Rhino to make 3D models. And of course, you can use some other 3D modeling softwares. And we also use Simplify 3D to translate 3D model into G code, which can be read by the machine. Then, we can free to print. But in our case, we'd like to explore silicon printing on textile. So we need a piece of textile which should have elasticity. And then we can pre-stretch it and fix it on the printing bed. After printing, the silicon should be cured at 60 degrees for at least an hour. Then the textile can be released. We will get a 3D structure. So this is basically our procedure. And the materials we need for this experiment, one is silicon and one is textile. The silicon we've been using coming from the printer company, which is a very flexible material. with low viscosity and very good flow behavior. So with all these properties, we can increase the design freedom of applications. About the textile, we've been using two kinds of textiles. One is lycra, the other is mesh. And they're both knitted fabric and super stretchy. And yeah, the difference is that the mesh has visible pores and the lycra is tightly knitted, which means when we printing, the silicon can easily running through the mesh fabric, but with lycra textile, yeah, it can just go in the pores instead of running through the pores. So with all this background, we start to print with very basic geometry patterns. And the first experiment is to print some wavy lines. So from the picture, we can clearly see that even with the same pattern, we can get totally different results just because the textile was pre-stretched into different directions. Also, on the right hand, we print a rectangular surface on lycra textile. And at the end, we got a finger-like structure. Yeah, the structure just shrink to a closed form. Yeah, and this model shows us not only the flexibility of the structure, but also the stability of it. To make this kind of model, we use the transformation first method, which means we print silicon directly on textile, and after cure, the silicon covered textile part will shrink together with the textile with the silicon. So this is how we turn a two-dimensional surface into a 3D structure. To take a step further, we're also wondering if we can create a 3D structure on textile. So we decided to put blue tape on it to separate some part of the silicon and textile. So as a result, we will get a partly silicon stick on textile structure and partly pop up. And for example, the model on the left. And with this model, if we stretch the textile vertically, then the pop-up structure will turn from state A to state B. If we stretch it in the other direction, then the pop-up will go back from B to A. So basically, this is a movable, reversible structure. Also, as a second sample, we print a rainbows pattern with cards on mesh fabric. We got a flip-up structure at the end, and the rainbows are all open in state A. If we stretch the mesh fabric vertically, the flip part will close to state B. So it's also a open closed structure. We can play with it. So
thank you, Xingwen. I'm taking over here. We've been showing you the model that we were interested in the beginning, and we used these tests that we have been doing to understand the material behavior better. And what you see is that we discovered that the pretension direction as well as the pretension as such are very important factors for a system. And for those of you who know the 4D textile research we have been presenting before, these are very important influencing factors that we have always when we have a look at a 4D textile. So with same structures, we can result in very different three-dimensional surfaces or the structures. But what you can also see on the right side, when we change the pretension, we have design parameters, and we're now deriving design parameters that allow us to define the shape, especially in the interaction between the textile and the silicon, resulting in these curved surfaces that you can see. And depending on the pre-stretch, the height can be adapted. And one more important part, and what was new for us as well, is working with silicon. It has very different processing, because usually you would heat up the silicon to up to 200 degrees in the process. And we have to leave out that process step because the textile wouldn't stay alive with this high temperatures. So we are curing it in the oven. And you can clearly see that we can also design shape definition by using different curing times or curing temperatures in relation to curing times to design this material adhesion between the silicon and the textile. We're happy that we presented now our research, and because we are a team of engineering, design, and physics, we are looking into maybe someone who would like to collaborate on the facts in the chemistry sector. We have a lot of interactions between the textile and the silicon, and in the silicon itself, which we would be interested in. And if someone is here interested, we would like to discuss further. And now we are happy for your questions or comments.